So welcome to the next topic, in fact our final topic for the year, Astrophysics, and it will apply to both triple and double science. So this is what we're going to have to learn by the end of this particular unit. Okay, so this is the first unit of 3 units. This is the first unit, the motion in the universe. Okay, so know that the universe is a large collection of billions of galaxies. A galaxy, define what a galaxy is, and also what our solar system is part of. Understand gravitational field strength, G, okay, and explain basically what this G is in terms of why it causes moons to orbit planets, causes the planets to orbit the sun, causes the moon and artificial satellites to orbit the Earth, and causes comets to orbit the sun. And then describe the differences in these orbits of these 3 different objects, comets, moons, and planets, and then use the relationship orbital speed equals 2 pi orbital radius divided by the time period t. Okay, so the solar system is where we're going to start. Okay, so the solar system basically consists of a sun orbited by 8 planets and their moons, some dwarf planets, along with many asteroids and comets. Notice that it's 8. It used to be 9, but Pluto is no longer considered a planet. It's only a planetoid. So now let's look at what these 8 planets are. Okay, so a planet essentially is a body that orbits the sun. It's big enough for its own gravity, and also that allows it to become round, and it has cleared its neighborhood of smaller objects around its orbit. So based on this definition, in 2006 it was defined that there is only 8 planets that orbit around our sun. Okay, and these 8 planets in order of distance from the sun are Mercury first, then Venus, followed by us on Earth, Mars, Jupiter the gas giant, Saturn with the rings, Uranus who also has rings, the blue planet, and Neptune, the blue planet. There are also a dwarf planet. Okay, so a dwarf planet is a celestial body orbiting the sun that is massive enough to be spherical as a result of its own gravity, but it's not cleared its neighboring region of other small bodies. And in our solar system, there are 5 dwarf planets. Okay, between Mars and Jupiter, there is Ceres, and beyond Neptune, there is Pluto, which used to be defined as a planet. Haumea, Makemake, and Eris, which is the largest. The next type of object in our solar system are the asteroids. Okay, an asteroid is a celestial body orbiting the sun that is not massive enough to be spherical due to its own gravity. Okay, and there's quite a number of these in the planet. Quite a number of these in the solar system. Most asteroids are actually found within an asteroid belt. Okay, and this is known very creatively as the asteroid belt. Okay, there's an example there of an asteroid called Vesta, which was taken in July 17th, 2011. So there is about 750,000 asteroids larger than 1 kilometer across. And there are also something called near-Earth asteroids, which by their name, because obviously astronomers and cosmologists are very creative, are called this because they are near the Earth. They pass very close to the Earth. Then we have the moons. Okay, so a moon orbits a planet. And you can see from the table here that Earth has its 1 moon, which we call very creatively the moon. Mars has 2, Jupiter has quite a number, 64, Saturn has 62, Uranus has 27, and Neptune has 13. Okay. A number of dwarf planets and asteroids also have moons, but they're still dwarf planets. For example, Pluto has 3 moons. So now we're going to develop towards an equation to describe at least the gravitational forces working on all these objects. And we'll start off with the first variable, capital T, the time period. This is the time it takes for a planet, or any object really, to complete one orbit around the Sun. And it increases with distance, obviously, from the Sun, because it takes longer because you're farther away. Okay, so Mercury, its time period is 88 days, quite a short time period. This is essentially what a year is. Okay, so a year on Mercury is 88 days. Venus is 225 days, okay, a bit shorter than us on Earth, which has a year as being a year. 365 days, except on leap years when it's 364. Mars, 2 years, it's again further away. 12 years for Jupiter, the gas giant. Saturn, 29 years, and Uranus, 84 years. And finally, the blue planet Neptune, 165 years, the longest distance away from the Sun, so the longest time period. So why are we discussing this time period? Well, it's all down to gravitational attraction. So the force of gravity is responsible for the orbits of the planets, moons, asteroids, and comets. Okay, so the moons, the asteroids and comets and planets are attracted to the Sun, and also the corresponding planets if you're a moon, and the Sun is slightly attracted to these particular celestial objects. So in 1687, Sir Isaac Newton stated the gravitational force is always attractive, would double if either the mass of the Sun or the planet was doubled, or the object basically, so replace planet with the celestial body up here. Okay, so depending on the mass of the asteroid, comet, or moon, and decreases by a factor of 4 as the distance between the Sun and the celestial body doubles. This is where we get gravitational field strength, which is lowercase g. Okay, it's a way of measuring how strong this force of gravity actually is, and this gravitational field strength is equal to the gravitational force exerted per a kilogram. Okay, so force is obviously in newtons and mass is in kilograms, so the field strength, the units are newtons per kilogram. Okay, so on Earth it's 10 newtons per kilogram. Okay, so it's 10 units of force per kilogram of matter. Okay, so in most cases field strength is in newtons per kilogram, which is the same as saying the acceleration due to gravity in meters per second. So basically in the gravitational field strength of Earth, an object will accelerate at 10 meters per second. Hence we use the same symbol, lowercase g. So this gravitational field strength G varies from planet to planet. Okay, so the force of gravity varies from planet to planet. It is greatest near the most massive objects, so you can think that Jupiter will have quite a large G. Okay, so on Earth it is 10 newtons per kilogram, which is our reference point. On the Moon, which of course is smaller than the Earth, it's going to be less. It's about 1.6 newtons per kilogram. On Mars, it's again a smaller planet, so it's about 3.7 kilograms, newtons per kilogram. Jupiter, which is a massive gas giant, is going to be about 2.5 times stronger in terms of gravitational field strength than us. Pluto, which is a really small little planetoid, it's 0.7 newtons per kilogram. And the Sun, which is a bit bigger, okay, a lot bigger than the Earth, is going to be 270 newtons per kilogram. It's about 27 times larger than the field strength of the Earth. So here's just a table illustrating summarizing basically the information that we've gone through. Okay, number of moons, the average distance from the Sun, how wide it is, which is a reflection of how big the sphere is, the time for a year, okay, the capital T, okay, so this is capital T here. The average surface temperature as a point of reference, so as you go further out it's going to get colder and colder because you're further away from the Sun, and the gravitational field strengths, okay, which you can see here. So these are just different atmospheric bodies, not just planets and planetoids. So in terms of orbits, the orbit of a planet is slightly squashed, so you might have thought of classically the orbit of a planet around the Sun would be a sphere. It's not quite that. It's actually a squashed circle called an ellipse, with the Sun being quite close to the center of the orbit, at least for planets. Okay, so the sun lies in something called the focus of the ellipse. Okay, so here is the sun, and it's basically not quite in the center of the ellipse, and here is the Earth orbiting around the sun. Okay, so planets move more quickly when they are closer to the sun, because obviously the attractive force between the sun and the object is greatest when they're closest together. Okay, so that's the nature of having an ellipse orbit. Okay, there are going to be times when it's going to be closer to the sun, like here, and times when it's going to be further away from the sun, like here. And it's going to be speeding up at this location, and I guess you'd say relatively slowing down at this location in the ellipse. Okay, so it's going to be faster here and slower here. Okay, which is what we've just discussed. Now, obviously, the above diagram is exaggerated. The nature of the ellipse is not quite as flat as that. It's more towards a spherical, but it's not a pure sphere. And obviously, the distances are greatly minimized in this diagram. I couldn't fit the entire orbit of the Earth around the sun in this scale on this slide. Okay, and also I couldn't fit the actual size of the sun or the Earth on this slide as well. Okay, so what would happen to an orbit without gravity? Okay, so as the planet, which is in this diagram, the color red, moves, it is continually pulled by gravity towards the sun. And to a lesser extent, because obviously of the mass difference, the sun is slightly pulled towards the planet. Okay, so there we go, there's the animation. So gravity therefore causes the planet to move along in a circular path and orbit. Okay, if there is no force of gravity acting, then the planet will continue to move along in a straight line at a tangent of its original orbit. Okay, so if you've seen the great British science fiction series Space 1999, you'll understand what happened when the moon lost the gravitational pull of the Earth. Okay, and it keeps going in a straight line. So comets are a special class of celestial body, similar to asteroids. A comet is a body of mass made of dust and ice that occupies a highly elongated orbit, which means that the time period is rather large. Okay, so when a comet passes close to the sun, obviously being frozen and getting closer to a warm object, the frozen gases tend to evaporate. This forms a long tail that shines in the sunlight. There we go, there's this elongated orbit of a particular comet. Okay, there we go. There he goes. Okay, so as it gets closer, the gases start to evaporate and it starts to form a tail. Okay, and as it leaves, the distance from the sun increases, that tail obviously stops forming, okay, and it just goes around being basically a ball of dust and ice. So comets are most visible and travel quickest when closest to the sun, and also we can see them because they're closer to us because we're on Earth. And comets are approximately in the range of about 30 kilometers, 15 kilometers in diameter. Quite small object. Okay, so Halley's Comet is the classic. Okay, I still remember seeing it in 1986. Excitement for me with my first telescope. And it's probably the most famous comet, which I'm sure you've all heard of. And it returns to the inner solar system every 75 or 76 years. So it last appeared when I saw it in 1986, and it's due to return in 2061. Now, obviously, because of the fact that it's losing this ice, which is evaporating, that tail's getting smaller. The comet itself is also getting smaller. So basically, the impressive comet that it was has slowly decreased over time. So I remember in my little my bedroom looking through the telescope at Halley's Comet. It was quite impressive because I had a telescope, but it was very difficult to see by the naked eye. Whereas earlier, when Halley, what the comet is named after, saw it, obviously it was a lot more impressive for him because it was 200 years earlier, and it was a lot larger and more impressive in terms of its tail of evaporating water. Okay, there you go. So 1705, so about 300 years ago. Okay, so it's been actually observed since 240 BC, and it would have been amazing to the naked eye by then because it would have been larger and releasing this longer tail. But over time, of course, it's slowly begun to melt, being less impressive. Okay, so to finish off this part of the topic, okay, let's just fill in these words. The solar system consists of a star, the sun, orbited by 8 planets, a number of dwarf planets, and millions of asteroids and comets. Of all these bodies orbit the sun because of gravitational force. Gravity is also responsible for the orbits of moons and artificial satellites. Most orbits are nearly circular ellipses, but those of comets are highly elongated. Comets move quickest when they are nearest the sun. Okay, so now moving forward with this equation, we'll now look at orbital speed, or v. So orbital speed is going to be 2 pi, the orbital radius of a celestial body, divided by the time period, which we've already looked at. Okay, so v equals 2 pi r divided by t. And orbital speed is meters per second, orbital radius is in meters, and time period is in seconds. Okay, so let's look at some questions to see if you actually have an understanding of how to apply this equation to problems. So calculate the orbital speed of the Earth around the Sun, given the orbital radius is 150 million kilometers. Okay, so there might be some conversions that you require to do. So pause the video now and see if you can answer the question. Right, so the equation we'll be using is v equals 2 pi r divided by t, of course. You plug in the numbers. Okay, so there's some conversions. For example, you have to convert year into seconds, okay, which is 31,536,000 seconds. And 150 kilometers is going to be converted into meters, obviously, so times it by 1,000, add another 3 zeros. So if you plug those numbers in, you'll get an orbital speed of about 30,000 meters per second. So you're never standing still, even though you're at that desk, you're traveling at 30,000 meters per second. Okay. So question 2, calculate the orbital speed of the moon around the Earth. Okay, and the orbital radius and orbit time are given. So it was about 30,000 meters per second for the Earth. Let's see how fast the moon orbits around the Earth. Okay, so again, v equals 2 pi r divided by t. Conversion again, and plug in the numbers. You should get an answer of about 1,000 meters per second, so a lot slower than we are traveling around the sun. Essentially because the sun is a lot bigger than the Earth, and yeah, the Earth is a lot, but the moon is a lot smaller than the Earth. Okay. And question 3, calculate the orbital speed of the International Space Station around the Earth, given the following values. Okay, orbital height of 355 kilometers, orbital time of 91 minutes, and the Earth radius of 6,378 kilometers. So this is a little bit tricky. Okay, so pause the video now and see if you can get the right answer. Right, so the orbital radius of the Earth is going to be the radius of the Earth plus the height it is above the Earth's surface. Okay, so about 6,733 kilometers. We then use the equation, converting, of course, 91 minutes into seconds, and plug in the appropriate numbers to give the answer, which is 7,748 meters per second. So it's really cranking it around the Earth, about the same as about 8 times the speed of the moon as it orbits around the Earth. Okay, so calculate the orbital time of a satellite as a speed of 3,075 meters per second and a height above the Earth of 35,906 kilometers, so quite a distance away from the Earth. And again, the Earth radius is given. So again, the orbit radius of the satellite, you have to add the two numbers together, the Earth radius plus the distance above the Earth of the satellite. Okay, then we use the equation, we have to rearrange it to get t equals 2 pi r over v, plug in the numbers, remembering the conversion of kilometers to meters, and it ends up being about 86,400 seconds. Okay, which is equal to about 1440 minutes or a day. Okay, so it takes about a day for this particular satellite to orbit around the Earth. So, since the last question involved satellites, we'll now focus on communication satellites. So these are usually placed in geostationary orbits, okay? So the last question, 24 hours, okay? That means essentially the satellite is always above the same place on the Earth because the Earth takes a day to rotate, okay? So that's an example of a geostationary satellite in the last question. Okay, so basically as the satellite moves, it moves essentially at the same rate as the Earth is moving or rotating, so it means that it's always above the same position on the Earth. Okay, so geostationary satellites must have orbits that take 24 hours to complete, circle in the same direction as the Earth's spin, are above the equator, and have an orbit of a height of about 36,000 kilometers, which allows them to do this 24-hour rotation. Okay, and basically it's used for communication satellites, including the satellite TV that you probably watch with your Netflix, and some weather satellites. Okay, so completing this part of the topic, a satellite is a lower mass object orbiting around a higher mass body. The larger the orbit of a satellite, the more slowly it moves and the longer it takes to complete one orbit. Geostationary satellites are used for communications and have an orbital period of 24 hours, and monitoring satellites normally use polar orbits. Okay, this is to finish off. Now let's look at our galaxy, the Milky Way. The Milky Way is the name of our galaxy, I've just said that. Okay, and that's what it looks like, very pretty. Okay, so if you're on a very dark sky, which you can get in Malaysia, because there's not much light pollution, at least at this part of the peninsula, you can actually see the Milky Way. And from the Earth, we see it basically edge on. In a very dark sky, it appears like a cloud across the sky, resembling a strip of spilt milk. Okay, so we're not the only galaxy. There's the Andromeda Galaxy. Okay, and a galaxy consists of billions of stars bound together by the force of gravity. Okay, there are thought to be about 200 billion galaxies in our universe, each containing about 2 billion stars. Really big numbers, kind of awe-inspiring in a way. And this is us, okay, the Sun, and its position on the Milky Way. So we're kind of on the edge of an arm of the spiraling Milky Way galaxy. Okay, so there are basically 4 types of galaxies defined by their shapes. Okay, you have the spiral galaxy, which is an example here of the Whirlpool galaxy. Then there's another form of the spiral galaxy called the barred spiral. Here's an example called NGC 1300. Now they're getting creative with their names. The Milky Way, our galaxy, is this kind of galaxy. We have the elliptical galaxy type, which here's an example, old classic M32. And the final one is an irregular one, which means it doesn't really fit within the other 3. And that's an example there called the Small Magellanic Cloud. The Large Magellanic Cloud is also very impressive. Okay, so just to finish that off, here are the words. The universe is made of billions of galaxies, which consist of galaxies of billions of stars, which are bound to each other by the force of gravity. The name of our galaxy is called the Milky Way. The Sun is located towards the outer edge of our galaxy, on one of those arms. There are 4 different types of galaxies. We've got the spiral, bar spiraled, elliptical, and irregular. The Milky Way is a bar spiral galaxy, and the Andromeda Galaxy is the nearest spiral galaxy to the Milky Way. There we go. So there are a few online simulations which you can try out for yourself. We're going to probably use a few in class just to reinforce the concepts. Okay, so just to finish off, here are 5 questions that you can use to give you an idea of what style of questions are asked in the exams. Okay, so outline the structure of a solar system will be the first one. Define what is meant by gravitational field strength. How is the orbit of a comet different from a planet? Give the equation for orbital speed and then use it to calculate the orbit of Mercury. And finally, what is the Milky Way? What are galaxies and how many galaxies are in the universe? Okay, so that's pretty much it for double award in terms of astrophysics. And for triple award, there are a couple more units which are more mathematically based and will help you with moving on to IB. So for double award, that's it for the course.